Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 12 for the course of Communication Technology. My name is Engineer Jaffar Ali and I will be your instructor for this course. As you know that in the last lecture 11 we started our discussion about pulse amplitude modulation, and keeping that context in mind, we will continue our discussion for the same topic in this lecture as well. Let's start with the recapitulation of the last lecture. So these were the slides of the last lecture in which we discussed about the introduction, that what are the possible approaches that we can use this digital modulation techniques, and what are the different variations that you can use in the digital modulation. The first one is known as PDM, or pulse duration modulation, or it is also known as PWM, pulse width modulation. The second one is PPM, that is pulse position modulation, and the third one which we are discussing right now is PM, that is pulse amplitude modulation. So we will also be covering the other two, PDM and PPM, but for now we will be just confined ourselves to this PM. PM was generally a signaling technique that was used to convey a message. This PAM pulses could be used, could be sampled amplitude values of analog signal, and this was the block diagram of the scheme of the PAM modulation technique. And I told you that everything is related to each other, and how these each individual module is important in the context of PM. And these were some equations that we used in the mathematical portion of the same topic. So the important point was one of the point was the detection technique in the use in the PAM model, and there are several techniques. The first one was optimum threshold technique, which we used in the data slicer, and we also discussed that how a synchronization is important when it comes to decoding the data of the received signal. And for that purpose you can also use different line coding techniques as well, or also this band pass filter, you can also use that as well. And if you are not using if you are not synchronizing your data at the receiving end side with the transmission end side, so you will get a phenomena of ISI, or also known as Intercember Interference. So how this will damage your data? I also told you that compression in time domain is basically expansion in frequency domain, and vice versa. It means that if you are extending let's suppose this received pulse at the slicer now extends over 4 bits of periods, so it will give rise to the ISI, or known as intercember interference. It means that in the time domain, when the first message is not received completely, the second message will be started downloading, so it will basically cause interference, or this interference is known as ISI, or intercember interference. You should probably call it ISI. This is the same acronym for the intercember interference, and you can see over here that the overall detection will be lost. You can see, let me highlight it for you. So the message signal here was, let's say there was no message signal at this point, it should be 0, but due to the ISI, the receiver detects both of these values, so it will take it as a 1. So there is an error over here. You can see that this is the error, and this error is caused because of ISI. So in the making decision modes of the detected data, ISI is a very important part, and for that synchronization plays a vital role in reducing the ISI. And this is the MATLAB plot that is generated for the ISI. So let's continue our discussion with Nyquist. This was the last topic we discussed. I told you that Nyquist criteria gives you a relief from the phenomena of ISI. What does Nyquist pulsing criteria or Nyquist pulsing shaping? So it is possible to eliminate the ISI at the sampling instance by ensuring that the received pulses satisfy the Nyquist pulse shaping criteria. So we will assume that for now, let's say TD is equal to 0. So the slider input is basically, you can see that given by the equation which I have just showed you right now. This is the equation, and if the received pulse is in such an order that if its value is 1 for n is equal to 0 and its value is 0 for n is equal to n not is equal to 0. So these are the two different criteria that you can use, and by putting the values of this h of n of t, you can get this rejected value, that is y of n. Y of n is the rejected value, and these other are the previous values, the final values, and the delayed versions of the same value, and also some other constants and variables. So to avoid ISI, the yn should be at least an plus v of n, and this equation should be satisfied if you want to ignore or completely avoid the ISI. So the condition is only achieved if this function becomes equal to t, and this is basically this equation is showing you the pulse spectrum excuse me, repeated at equal interval of symbol rates, sum to a constant value of t of all frequencies. So if you want to completely ignore ISI, so you have to follow this condition and you have to satisfy this condition. So there are some conditions that you have to achieve in order to avoid ISI completely. So this you can let's see in the diagram over here. This is the function of h of f, and the time for the height of this is t, and this is the frequency domain. You can see that clearly it's on the x-axis is given by the frequency. So you can see that there is a huge ISI over here. You can see that there is one symbol is not completely finished and the other one is started decoding itself. So this is we can clearly see that here is the ISI, and you can see that simple h of t, we have also discussed that why it's possible to have a train of pulses, because the data is coming right inside the receiver, and the receiver forwards into the decoder without any delay. So you can see that the equations are given over here. This is the s domain, basically time domain, and this is given by the delayed versions of the impulse function. Impulse function, you know that impulse function is basically just a peak or just a hike like this. This is the impulse function, and these are the delayed versions of these impulses. So the spectrum, and you can see over the diagram over here, these are the I was telling you about these was the hikes. You can see that these are the hikes, or you can say the impulse pulses, which when multiplied by this equation h of t, you get something like this wave. So we have to follow the Nyquist criteria, and once we follow the Nyquist criteria, you can see that no pulse bandwidth less than 1/2t can satisfy this criteria. If you if you reduce the bandwidth less than 1/2t, that is half of t, you can never satisfy this criteria. So in order to satisfy your criteria, your bandwidth must be less than 1/2t. So for this purpose, the spectrum, after you apply this, the spectrum will not be repeat itself at a constant value and do not sum to a constant value. So the minimum bandwidth required for pulse spectrum in a rectangular, for say of argument, let's say a rectangular spectral shape, so it should have a sinc pulse response error time domain. So now what is sinc function? Sinc function, let me draw it for you. Sinc function is basically a function which is like this. Let me draw it for you first. and it reduces itself at plus infinity and as well as at minus infinity. It becomes 0 as well over here in the same shape. So this is a sinc function. So sinc pulse shape is very sensitive to errors in sampling time owing to its low rate of side oblate decay. So you have to also keep in mind that your pulse should be in the sinc, because sinc is the most sensitive shape when it's come to decoding. There are several shapes of pulses. I have told you about the square shape, the rectangular shape, the triangular shape, the sawtooth shape, and there's a sinusoidals, of course. But among all of these, the sinc function or the sinc pulse is basically the very sensitive when it comes to detecting errors, because it has a high peak over here and there are several low peaks over here. So you can easily compare that this is a decaying function. So you can see that the side lobe is currently is decaying. So that's also mentioned in the definition over here. You can see that. So what is the hurdle in making the Nyquist pulse shaping which makes it a bit difficult? So the first thing is the practical design. So it is hard to practical design a brick wall filters. Consequently, filters with smooth spectral roll-off are preferred. So I've already mentioned in the previous lecture that there are some issues for which we do not use BPF, or you can call it band pass filter. And the first one was on the practical approach or the design, because you know that the filters do not have very sharp cutoff due to which we have to include some of the noises that are coming at low other frequencies as well, other than your required frequency. So pulses may take values from t less than 0, or you can call it non-causal system. A non-causal system are those systems which starts giving output before it gets some input. So it means that there are systems that are there which give you output before you have given even any input. So these kind of systems are known as non-causal systems, and pulses may take values for that as well. So no problem in practical system, because delays can be introduced to enable the approximate realization, and for that you have to use just a delay. You can hold your data for a certain amount of time, and for that you can use delay in your side of the case. Now you can see that these are the casual responses. So these were all of these two are basically values. You can see that this is the actually non-causal response, because at time is equal to 0 it is possible to get a value, let's say this value, but at time is equal to minus, you are not even there, you are not giving even a single input. So how can you get output? So for that system you can use a delay function, and you can basically create a delay. So you can see that the systems in the first case it was starting from here, but in this case the system is starting from here. You can see that the system is starting from here. So this is you make the system a causal response, and there is a certain amount of delay as well introduced, that is 10 seconds. So you have given a delay of 10 seconds and then you have started whatever you are doing. So this is basically a causal response, and how you can make a system non-causal to causal just to introduce a delay. We will also discuss these topics. You can see that these topics are somewhat relevant from your previous courses, and and some of these topics like this causal system will also be there when we will be studying control system in your last semester. So you have to keep all of these topics in your mind and try to connect these dots when you are trying to understand any problem in your whole program of this 4 year. This is the RC, or raised cosine follow-up pulse shaping. This is another criteria. We have discussed two of the criteria or two of the pulse shaping methodology. The first one was BPF and the second one was Nyquist criteria, Nyquist pulse shape criteria. And the third one is basically RC fall of pulse shaping. The RC stands for raised cosine wave. So practically important pulses shapes which satisfy the criteria are those with RC roll-off. The pulse spectrum is given by the equation which is mentioned over here, and there are three. In the first part there was in the RC criteria there was two methodologies, but or two, you can say, given outputs for a single input, but now you can get three outputs. If the output is 0, so it means that and the condition is mentioned over here as well, and there are three outputs. The one is t cos square pi by 4b beta, and this is 0. So the general RC function is as follows. You can see that this is your rectangular kind of wave, but not completely rectangular. So you can also see that this equation has to satisfy this equation. I'll also discuss a type of a trade-off between this thing. So the corresponding time domain pulse is given by h of t sine pi by capital T, that is the time period of the whole wave, into the t, that is the instantaneous time, and divided by the same function. This is becomes a sinc function. You can see that this is a sinc function over here. The equation of sinc function is similar to like this, and this is the function of cos. So now there is a trade-off. Now B allows a trade-off between a bandwidth and the pulse decay rate. Sometimes B is normalized as this equation, and these all equations are from your book, and if you want to see how these are driven, so you can consult your book and you can see the derivation over there as well. And if you want to also derive these equations, so it is not a part of this course, but you can also do it for your practice as well. So let's discuss the plots over here. You can see that in this we have done RC shaping, RC pulse shaping. So this is the normalized spectrum of h of f of t. This was a completely rectangular wave, and we have made it, and the pulse shape is mentioned over here. You can see that the pulse shape is basically sinc function, which basically I told you that sinc function is a function which has a peak and then started decaying on both hand sides like this. Similarly, let's talk about this function. This is not a completely rectangular wave, but for sake, let's say this is a function, and if you make it a complete pulse, you will get something like this. So now you can see that the difference between these two specifically is the side lobes, which is not relevant to you. So means the main theme is the pulse. That is the same for both of these waves, and the only difference is between in the side lobes that are there. And if you see that this wave, this has the same main component, the peak, or you can say the pulse, and the only difference is the side lobes. Here is a flat side lobe on the both hand sides. So this is basically RC pulse shaping, in which you used basically a cosine filter, or you can say a cosine wave and sinc wave, a combination of both of these, and you can do the trade-off. And this is the diagram, or the eye diagram. You can see that. So normally in the BS I never teach the eye diagram, but here for now, because it is impossible to draw these diagrams in the whiteboard in the class, but now as we are going towards going with the online education, and when the computer is there for everyone, so it is easier to provide you just a brief introduction of the eye diagram. So eye diagram is basically the main output when you have to study or analyze the spectrum or in the frequency domain. So you can use the eye diagram. You can see that this same thing in the computer is you can draw this into the whiteboard, but you cannot draw this eye diagram because it's a kind of 3D diagram, and it provides you a figure of eye. So it means that the area, you can see that there is a density. So the density, as the density increases, it means there is a high chance of the ISI in this portion. Similarly, in this portion, You can see that in this portion there are high ISI. So you can see that there is not as much density, so the eye lines are not that much of density. And let's talk about the main important topic for the we are basically going towards the end of the discussion of the PM. So probability of error. So in the presence of noise, there is a smart chance or a quite of the chance that the decision errors are there at the slicer input. So the smaller the I, the higher the chance of the noise that the noise will cause an error. For a binary system, a transmitted, let's say 1 could be detected as 0, and a detected transmitted 0 can be detected as 1. So these are the errors that you can get. So in a pan system, the probability of error is given by P of E is equal to probability of a received sample is incorrectly detected. So for a binary system, PE is known as the probability of error or the bit error rate. So these two terms you have to these two basically symbols you have to keep in mind, P of E and BER. So what is BER? Normally I'll just try to make you understand in a very short example. Normally in let's say you have developed a communication system, and if you want to judge that how much my system is efficient in terms of the error rate, so normally people make it very clear that my error rate or BER is equal to 10 power minus 6. It means that 1 out of 1 million, or let's say this is 1 million. So 1 out of 1 million you will get one error. So there is a chance of one error when you have transmitted 1 million bits. So normally people call it something like this. And then smaller the value of BER, the good the system is. If any system is there with 10 power minus 9 of BER, so this system is much more efficient as compared to this system. So this is the theoretical portion which is mentioned over here. The equation is given by V of n is equal to Vi plus Vn, where Vi is the received value and Vi is equal to V0 for a transmitted 0 and Vi is equal to V1 for a transmitted 1. With 0 ISI and an overall unity gain, Vi is equal to Vn, the current transmitted signal binary symbol. Suppose that and in this case we have supposed that noise is Gaussian, and with zero mean and the variance is equal to sigma V square. So these are the assumptions that we have to make. There are certain type of noises. The very famous one is known as the Gaussian noise. The worst one is I will just give you an idea about this. It is known as AWGN, Avogadro Void Gaussian noise. So this is the worst ever noise you can you can expect from any of the communication system. So there is other kind of models, fading models, also known as relay model, and there are several models. You can discuss it and you can also Google it. We are just assuming that for a Gaussian system, for a noise with a Gaussian system, and the zero mean and the variance of this equation will work brilliantly. So this is the equation where f of v denotes the probability density function PDF, that is this is the function, and this equation is equal to 1 divided by, so there is no need to memorize these equations, just it is the course of this BER discussion will be end over here. This is just to give you a clear idea about the further, if you want to go further, how can you go and proceed your study about the BER. So BER is a function that is basically there, and you can also study it with the PDF, or known as probability density function. So you can see that this is the you can see the graph of the BER in terms of PDF. So this is your PDF, sorry, this is your yes, PDF, and these are certain values that are there when you want to calculate your BER in terms of graph. So Now let's talk about this diagram. This diagram is very much important because you have to understand it because it's the basic concept behind the BER. So the basic phenomena that on which BER works is the conditional probability. Now what is the conditional probability? Let's say you have received y of n but you sent 0 of n. Now if this y of n was 0 that you received is 0, so it means there is no error. Let me discuss it again. Let me explain it again. Let's say you have received you have transmitted 0 and you have received y, and if this y is 0, so there is no error. But if this y is equal to 1, so there is a chance of error. Similarly, you received y and you sent 1. Now if this y is 1, there is no error. But if this y is 0, there is an error. So let's draw the PDF of both of these equations or both of these functions, because this is the PDF graph. So this is the graph of V0 and this is the graph of V1, where 1 was sent and 0 was sent. So the graph is basically overlapped. You can see that these are overlapped over here, and this is the VT, this is the threshold. You can see that I have discussed it over here. VT, this is VT. VT is basically nothing but V0 plus V1 divided by 2. This is a basically threshold value that is approximately in the center, but it's not always the case. So if this value is basically over this side, you will get an error, and if the value is basically on this side, you will get an error. So this is basically a concept. You can see that if the point is, let's say, over here, so it means that you have sent 0, but you have received 1. And if you have at this point, it means that you have sent 1 but you have received an error. It means you have received a 0. So these are the graphs, and this is the basic concept behind the BER. So this is all about today. I hope that you have understood the remaining topics of PAM quite a lot in this lecture. I hope that you will also bring some good questions in the coming class, because you know that I believe that the more you ask, the more you learn. I'll see you in the class inshallah tomorrow. Thank you very much for watching. Allah Hafiz.